Hi guys. Well, section 2. We're done with 1. Forget about it. It's done. Section 2. Atoms, molecules, and ions. So section 2 is kind of like chapter 2. The reason I don't name them chapters is because everyone's chapters are a little bit different. Not much. Very, very close. But just to be safe, instead of chapters, I call them sections. So this is section 2, atoms, molecules, and ions. Now, in this video and some of the earlier videos for section 2, we're going to talk about some of the history, okay? People like Rutherford and Dalton and Lavoisier and Mendeleev, and there's some other one, J.J. Thomson. Some of these guys and just some of the history of the atom, discovery of the nucleus, discovery of the electron, etc. Okay, because this all takes place in your chapter 2s for the most part. So I want to make sure I get to it. All right. So section 2, atoms, molecules, and ions. All right, let's get started. There are 3 fundamental chemical laws to be aware of. Number 1 is the law of conservation of mass, and I'm drawing a sample down here. Law of conservation of mass states that matter is neither created nor destroyed. This is credited to Lavoisier, who was around from 1743 to 1794, in case you were wondering. So I put a box around this equation. On the left-hand side, 4 H's, 2 O's. On the right-hand side, 4 H's, 2 O's. Okay, this is why we balance equations, because of the law of conservation of mass. Okay? Number 2, this is the law of definite proportions. All right? Now, I do have a trick to this, but the next one is going to be the law of multiple proportions. So I do have a little bit of a trick, some verbiage I use to remember the difference between the law of definite proportions that we're talking about now and the next one. First things first, number 2, the law of definite proportions. A given compound always contains exactly the same proportion or ratio of elements by mass. Okay? For example, why don't we consider a very popular molecule? Let's consider water. Water is H2O. Okay? In that one definite compound, there's always a ratio of 2 hydrogens to 1 oxygen by mass. So if you look up hydrogen on the periodic table, it weighs 1.01. Oxygen on the periodic table weighs 16. Okay, so of that 18.02 total mass, H2O is always responsible, hydrogen is always responsible for 11.2% of that mass. Oxygen's always responsible for 88.8% of that mass. I can put it much more simply, and I'm going to do it right now. It says, in other words, the ratio of hydrogen to oxygen atoms in water, no matter how much the sample size, how small the sample size, how large, the ratio is always 2 hydrogens to 1 oxygen. Okay, so the ratio is always 2H to 1 oxygen in that one definite compound, H2O. Okay, see how I use the word definite there? There's one compound, one definite compound. All right, so that'll be helpful when we get to the third law, law of multiple proportions. All right, another name, we've heard of Lavoisier, now John Dalton. When John Dalton was on his way to discovering the atom, he stumbled into and thus discovered the next fundamental law, okay? And this is number 3. This is the law of multiple proportions. As you might expect, we're going to need multiple compounds, unlike the law of definite proportions where we were talking about one definite compound. The law of multiple proportions. It says, when 2 elements form, that should say form and not from, when 2 elements form a series of compounds, the ratios of the second elements that combine with the first element in the compound, they can be reduced to small whole number ratios. Let me read that from the top. When two elements form a series of compounds, the ratios of the second elements that combine with the first element can be reduced to small whole number ratios. Here is an example using how many compounds? 2, but let's refer to them as multiple compounds. Look at the oxygens. We're taking a look at the second element. The ratio of oxygens is 2 to 1. So it's 2 oxygens on the right for every 1 oxygen on the left per that 1 carbon. Okay? So I can have CO or CO2, but you would never be able to see CO and CO 1.5. Has to be a whole number integer. Okay? Whole number ratio. So first bullet point, in the multiple compounds, the ratio of oxygen atoms per the 1 carbon is 2 O's to 1 O. So unlike the law of definite proportions, here we are considering multiple compounds, and the ratio is between the same element, just in different compounds. Okay? Law of definite proportions, we had our example was 2 H's to 1 oxygen, different elements. One definite compound, different elements. Here it's the same element that you're making comparisons to. So it's 2 oxygens for every 1 oxygen in the multiple compounds. All right, so hopefully that clarifies it up a little bit. You can see how there's kind of, in your head, they can kind of flow over unless you have the 2 in front of you for comparison. All right, so we've got the law of conservation of mass, we've got the law of definite proportions, and the law of multiple proportions. Okay, so with that, in this little bullet point here, it says, Dalton began to think that because there was always whole number multiples, there must be some simple unit, and this unit he called the atom. All right? So that led him to propose his atomic theory, and we'll get to that very, very soon in the next page, I believe. But his atomic theory is it's got 5 little listings, 5 postulates there, and we'll get to that. But regarding the unit that I have in quotes, for example, this is what Dalton believed. He thought one cannot have CO 1.5 because you cannot have 0.5 of a unit. You can't have half of an atom. And he was right about that, and he's still right to this day. Okay? Some of his postulates that are coming up are wrong, but only 2 of the 5 needs to be fixed ever so slightly, and we'll get to that. First, let's do this sample problem. So top of our new page of notes here, it says, consider 3 compounds that consist of only nitrogen and oxygen. We have a compound X, we're going to have a compound Y, and a compound Z. Okay? It says compound X consists of 1.750 grams of nitrogen and 1 gram of oxygen. Compound Y consists of 0.8750 grams of nitrogen and still that 1 gram of oxygen. Compound Z consists of 0.4375 grams of nitrogen and, you guessed it, that 1 gram of oxygen still. All right, our objective is to show how this data illustrates the law of multiple proportions. Well, if we want to show the law of multiple proportions, we have to show that the nitrogens are all in whole number ratios to each other. Okay? So it says, well, we need to compare the ratio of nitrogen atoms by mass in the 3 compounds X, Y, and Z. Okay? The oxygen is kind of like the placeholder. It's kind of like the C was in CO and CO2 in our previous example. So if I do X divided by Y, 1.750 grams of nitrogen divided by 0.8750 grams, 2 to 1. The ratio of nitrogen atoms in Y to Z is also 2 to 1. And then the ratio of nitrogen atoms in compound X to compound Z is 1.75 grams divided by 0.4375 grams. 4 to 1. Small whole number ratios. Okay, so all we did was write three proportions there: x over y, y over z, x over z, and we were able to prove that yes, this illustrates the law of multiple proportions. All right. Okay, so now, and I spoke a little bit earlier about this, but now I want to talk about Dalton's atomic theory. He's got 5 postulates or 5 statements, okay? And he did this a long time ago, and only 2 of those 5 statements need to be corrected slightly. So, 200 plus years ago, okay? Dalton's atomic theory. In 1808, John Dalton explained the 3 laws just discussed with his atomic theory. Okay, today we refer to it as Dalton's atomic theory. Now, that atomic theory includes the following 5 concepts. Okay, 5 statements, 5 postulates, 5 concepts, whatever you want to call it. There's 5 listings here that he makes. Okay, number 1, each element is composed of tiny, indestructible particles called atoms. Now remember, this is like, atoms is a new word, okay? This is like he's kind of saying, hey, there's something there, that this repeatable unit that cannot be broken down further is called the atom. So number 1, each element is composed of tiny, indestructible particles called atoms. Number 2, the atoms of a given element are identical. The atoms of different elements are different. Okay. Concept number 3. Compounds are formed when atoms of different elements are combined. A given compound always has the same relative numbers and types of atoms. That's the law of definite proportions, right? So let me read number 3. Well, I ran out of time there, but number 3 is the law of definite proportions being kind of, he's summarizing the law of definite proportions. Now, in number 4, it says, chemical reactions involve the reorganization of atoms. But the atoms themselves are not changed during the process. Okay, this is he's hinting at the law of conservation of mass. Okay, whatever you start with on the left-hand side with the reactants and you rearrange everybody, you have to have the same number and types of atoms on the right that you started with. Law of conservation of mass. Number 5, atoms cannot be divided any further. Okay, well, while we have number 5 in front of us, we do know that this one is not correct. Atoms can be divided further, right? Protons, neutrons, electrons. Also, on the previous page, if I say the word isotopes, okay, that should help you maybe hone in on one of 1, 2, and 3 that needs to be fixed. Okay, I'm going to talk about that right now. 200 years later, Dalton's atomic theory only has 2 modifications that must be made. In step 2 above, atoms of a given element are not always identical. Okay, we can have atoms of the same element, and some atoms have different numbers of neutrons. Okay, this is called isotopes. We'll talk about isotopes as we move further through the course. Now, in step 5, this is one I just mentioned. In step 5 above, atoms can be divided further into the 3 subatomic particles: protons, electrons, and neutrons. All right, so let's write that down so we have it in our notes. Proton, electron, and neutron. All right. Okay, so let's move to a new page here. And this new page is, there's no notes here. I'm just kind of letting you guys know that in our next video, right, video number 2 for section 2, we're going to talk about some early experiments to characterize the atom. All right, that's coming up next. Stick around. This is section 2, video number 2, coming up next.